In Chapter 15, Section 6, we're going to look at triple integrals. So we have one right out the gate that says take the antiderivative of 0 to 2, then x to 2x, then 0 to y of the function 17xyz dz dy dx. So the order of those derivatives is going to tell us what's the variable and what's constant. So we work inside out. So the first thing we're going to look at is dz. Therefore, the only variable there is z. Everything else is a constant. So we can write this as 0 to 2, x to 2x of 17xy, pull those out, the antiderivative from 0 to y of z dz dy dx. And now we'll take the antiderivative of that, leaving everything else the same, and we'll get z squared over 2 from 0 to y. And let's pull out the 17 and the 1/2. So this is going to be 17 over 2, 0 to 2, x to 2x of, plug in y, let's see here, 17, let's put the x and y in here, and then it's going to be y squared upper limit minus 0 squared lower limit. I pulled the 1/2 out, so that's no longer there, and it's dy dx. So now we get 17 halves, 0 to 2, x to 2x of, we're going to have x times y to the third, y1 times y squared, and then we're dealing with dy dx. So this is going to be 17 halves, antiderivative of 0 to 2 of x y to the fourth over 4. So now only y is a variable, and x and 17 halves is just a constant, and the antiderivative of y to the third is y to the fourth over 4. And we're evaluating that from x to 2x dx. So this is going to give us, I'm going to factor the 1/4 out, so we're going to get 17 over 8, 0 to 2, x times 2x to the fourth minus x to the fourth. And then that's going to be dx. And notice everything is in terms of x now, as it should be. And we're going to have 17 over 8, antiderivative from 0 to 2. 2x to the fourth is 16x4. I guess I'll write this. X 16x4 minus x4 dx. So that's 17 halves, antiderivative of 0 to 2 of 16 minus 1 is 15 times this x out here. So it's going to be 15x to the fifth dx. This antiderivative would be 15x to the sixth over 6 from 0 to 2. And if we multiply all of that out, we're going to get 17 times 15 divided by 2 times 6. And you should get, for some reason I wrote this as a 2, it's supposed to be an 8 over here, 8. So we're going to get 17 times 15 over 6 times 8, so it should be 255 over 48 times 2 to the 6th minus 0 to the 6th. And you're going to get 2 to the 6th times 255 divided by 48 should simplify nicely to 340. Okay, so that would be problem 1, the first example of a triple integral, and we just had to be careful we're ourselves inside, outside, and anything that's not a z in the first case is a constant, anything that's not a y in the second case is a constant, and then we should end up with just numbers at the end if it's balanced correctly. Problem 1. Okay, in problem 2, they're going to make us set up the integral ourselves. So they have this region E, and they say E is bound by x, y, and z, where x varies from 0 to 1, y varies from 0 to x, and z varies from x to 2x. So we're going to set this up like this. Now, almost always, the variable that's bound by numbers will go last. So we're going to have 0 to 1, which is the x term. That's going to go last, so we're going to end this with dx. And let me actually write that further to the right because I don't know how much space I'm going to need. Okay, and then it just so happens that this is not always the case. The second variable we're going to use is y, so it goes from 0 to x, so we're going to go with dy. And then the last one is going to be dz. Notice it's the last one I'm tackling, but it's actually the first one we're going to do. So it's going to go from x to 2x. And the function they want is this. 17 yz cosine of 10x to the 5th. And dv in this case is just the dx, dy, dz that we have. Or dz, dy, dx in the proper order. Okay, so in the first case we're only dealing with z. So this is going to be the antiderivative 0 to 1, 0 to x, of 17y z squared over 2, the antiderivative of z, times cosine of 10x to the 5th. It's supposed to be a 10 right there. And we're evaluating that from x to 2x. So we're going to get, let me pull the 17 halves all the way to the front. 0 to 1, 0 to x, of y times 2x squared minus x squared, upper limit plugged into z squared minus lower limit put into z squared, and then we have the cosine of 10x5 still out here, and now we're done with z, so it's just dy dx. Well, this is going to give us 17 over 2, 0 to 1, 0 to x, and we're going to get 4x squared minus 1x squared, which is going to be 3x squared times y, times cosine of 10x5. And now we're doing with respect to y. So this 3 can come out again, and that's going to make it 51. So this is going to equal 51 over 2, 0 to 1. X squared stays the same, it's a constant. Y, the antiderivative of that, becomes y squared over 2. And that is being evaluated from 0 to x. Then we have the cosine 10x5, and we have dx. This is going to give us 51 over 4, so I'm going to pull this 2 out here. And we're going to have antiderivative 0 to 1, x squared times the quantity x squared minus 0 squared. And then we have the cosine of 10x5 dx. Okay, this is going to equal 51 over 4 antiderivative 0 to 1 of x to the 4th times cosine of 10x5 dx. Okay, now to do this one, we have to use u substitution. So we're going to let u equal 10x5. Therefore, the derivative of u will equal 50x to the 4th dx, and therefore dx will be du over, du over 50x4. And let's substitute in the limits. So we're going to get u of 0 is 10 times 0 to the 5th, which is just 0. And u of 1 is 10 times 1 to the 5th, which is 10. So we will change our limits so we don't have to back substitute at the end. So we're going to get 51 over 4. Now the limits are 0 to 10, and it's x4 times cosine of 10x5, but 10x5 is u, times dx, but dx is really du over 50 x to the 4th. And like I've been saying, if we've done our u substitution correctly, all the non-u terms should go away. So x4 on top, x4 on bottom. I'm going to pull the 50 into this 4. We will get 51 over 200, 50 times 4, antiderivative of 0 to 10 of simply cosine u du. Well, the antiderivative of cosine u is sine u, and we do not have to change u back to 10x5 because we changed the limits. So that's evaluated from 0 to 10. So this is 51 over 200 times sine of 10 minus sine of 0, the lower limit. But sine of 0 is 0. So this whole thing will collapse to 51 over 200 times the sine of 10. Some number, but putting it with exact values, you would get that. Be problem 2. Okay, problem 3 is fairly similar. They want us to calculate the triple integral of this function 5xy on dv. So let's start to set this up. It's 5xy under the plane z equals 1 plus x plus y, and above the region of the xy plane bounded by the curves y equals root x, y equals 0, and x equal 1. So what we're going to do is we're going to start with z. So we're going to go dz. Well, z is going to vary from 0 to this equation, 1 plus x plus y. Then we're going to go dy. Y varies from 0 to square root x. And then x, it says, equals 1. But the only way x can equal 1 in this is if we started at 0 and then we go to 1. Okay, so that's the hard part, is getting these limits set up because they don't do it for you. And so if we set it up like this, we will get, the first antiderivative is easy, 0 to 1, 0 root x. There is no z, so we just add a z. So let me pull the 5 out. So pull the 5 out, and it's going to be x, y, z. So this dz turns into a z. And then, oops, I forgot one here, dx is last. So now we have, this varies from 0 to 1 plus x plus y, and then we have dy dx. This is going to be 5, 0 to 1, 0 to root x of x times y, but z is going to be first 1 plus x plus y, then minus, it's going to be 0, the lower limit, dy dx. And we have to distribute this xy into these three terms. So we're going to get 5, 0 to 1, 0 to root x of xy times 1 plus xy times x, which would be x squared y, plus xy times y, which is x times y squared. And then the minus 0 drops away with respect to y, then x. So now dy this is a variable, this is a variable, that's a variable. All those x's are constants. So the antiderivative would be 5, 0 to 1, x y squared over 2 plus x squared y squared over 2 plus x y cubed over 3, and that is going from 0 to root x, and then it's dx. So this is going to be 5, antiderivative 0 to 1 of x, plug in root x, so you get root x squared over 2, plus x squared times root x squared over 2, plus x times root x to the third over 3. And then that's the upper limit, so we just got that one. Now it should be minus the lower limit of 0, but that 0 is going to just take away all the 3 terms, so there's nothing in that it contributes. So this is dx. Okay, so this is going to be 5, 0 to 1. These square root x squareds are going to be x, but there's an x there, so this is going to be 1/2 x squared. And then this one's going to be 1/2 x cubed, because we have an x squared here, and then we have the square root of x squared, which is x, so we have 3 x's. This one is going to be 1/3 x raised to the, so x raised to the 1/2 raised to the third is 3/2, but this is x to the 1, so this is really x to the 5/2. So we have 3/2 plus 1, which would be 3/2 plus 2/2, which is 5/2. Okay, dx. All right, so now we take the antiderivative of that. 5, oops, we're taking the antiderivative, so the symbol's gone. This is going to be 1/2 times x3 over 3. This is going to be plus 1/2 times x4 over 4 plus 1/3 times x to the 7/2 divided by 7/2. And that's going from 0 to 1. Okay, so this is going to be 5. This will be 1/6 times 1 to the third plus 1/8 times 1 to the fourth. They gave us nice numbers here. 1 and 0 are really easy to plug in. This is going to be, this 2 right here is going to flip to the top. This 7 is going to combine with this 3, so it's going to be 2 over 21, 1 to the 7/2. But those are all just 1s. So this is just at the end 5 times 1/6 plus 1/8 plus 2 over 21. And the 0 lower limit will not even factor in. So if you add these correctly with the lowest common denominator and multiply by 5, you should get, at least for my numbers, 325 over 168. Okay, so not too bad. It's just the limits get a little messy with all the fractions and everything, but just take your time and make sure you account for everything correctly. You know, adding fractions and all that, so you should be able to get there. That's problem 3. Okay, problem 4, it kind of helps to draw the picture. So we've got the triple integral of 4z dv, which stands for this 3-dimensional volume, where E is bounded by the cylinder y squared plus z squared equal 9, and the planes x equals 0, y equals 3x, and z equals 0. Okay, so let's see if we can draw this. Okay, the cylinder y squared plus z squared equals 9. Y squared plus z squared equals 9 would be a circular cylinder in the YZ plane that would go out towards, it actually goes away from us and towards us along the x-axis. So this is the cylinder. Okay, so that's that part. And the plane's x equals 0. X equal to 0 is this back plane here. So that's where it stops, so it's not going to go further into the page. Y equal to 3x. So this is actually a plane. Y equal to 3x is a straight line plane that's going to go through like this. And it's basically going to slice this cylinder. It's hard to draw. So we've got this plane, y equals 3x. It's going to slice through that cylinder. And then z equal to 0 is going to only take it's going to cut off the bottom of this cylinder. It's only going to allow stuff above the xy plane. So let me clean this drawing up. So what we should end up with is a cylinder that looks like this. So it's going to come down to the y-axis, then it's going to come down to the line y equals 3x, and then it's going to go back to the origin and up. So it kind of looks like this orange slice, or like a slice of fruit that's been cut in half. So this is the shape we have. That's the volume we're going to integrate. Okay, so let's see if we can piece out what would be what here. So if y squared plus z squared equals 9, that means the original circle of this would go to 3. So this is like 3 squared. So this radius here is 3. So it's going to go up to 3 units on the z-axis. Okay, what else do we have? This line right here is defined by y equal to 3x. Okay, where it touches the y-axis is going to be the point. This is going to go to the point y equals 3, also based on this radius here. Now, if this goes to y equals 3, and this point is y equals 3x, then this x value, the most it can be is 1. So only can I get a value, if I plug in a value of 1 for x, I'll get that y equals 3. So that's what this point is. Okay, so based on that, we're going to set up our integral, and we're going to have triple integral of this kind of wedge here, and it's going to be, the original form was 4z, so it's going to be 4z, and then we're going to want to notice that x varies by 3 and 3x, or I should say y varies by 3 and 3x, and z varies by this kind of complex formula. So if we solve this for z, z is 9 minus y squared, z squares that, so z is square root of 9 minus y squared. Now we don't need plus or minus there because we've cut off the left hemisphere, which would be negative, and the bottom set of octants, which would be also negative. So we're in the first octant here, so everything's positive. So we are going to start with z. In fact, z is going to vary from 0 to this square root of 9 minus y squared. Now this is kind of a hint. If the first limits are a function of y, then we want to do y next. And y varies from 3x to 3. And then the last value will be dx, and that varies from 0 to 1. So x will start at the origin, the biggest it gets is 1. Okay, so let me just double check. And yes, that looks correct. Okay, so that is definitely the hard part, is setting this up. Now, taking the antiderivative hopefully isn't too bad, but let's go through it. So pull the 4 all the way to the front, 0 to 1, 3x to 3. Antiderivative of z would be z squared over 2. And we're plugging in 0, and we're plugging in the square root of 9 minus y squared. Then we have dy dx. Okay, when we plug in let me pull this 2 out here. This would be 4 over 2. Pull this 2 out. And we have z squared, but when we plug in the upper limit, that's really going to be the square root of 9 minus y squared squared, minus 0 squared. Then it's dy dx. Well, this is going to equal 4 over 2 is 2, 0 to 1, 3x to x, and that square root and that square will just cancel, so it's 9 minus y squared dy dx. And the 0 is just going to completely go away. Okay, now we can take this antiderivative. It's 2, 0 to 1, 9y minus y to the third over 3. That varies from 3x to x dx. This is going to give us 2. It's going to be 9 times x minus x cubed over 3 minus, plug in 3x, so it's going to be 27x minus 27x cubed over 3. So you've got to cube the 3, which makes it 27, cube the x, which makes it x cubed, and that's over 3. So this is going to be 2, 0 to 1 of 9x minus x cubed over 3 minus 27x plus, make sure my minuses are right, 27 over 3 is 9, so it's 9x to the third dx. Okay, what can we combine here? We're going to get 2, 0 to 1. 9x take away 27x is minus 18x. And 9x cubed minus 1/3 x cubed is 27x cubed over 3 minus 1. This would be plus 26 over 3x to the third dx. And when we take the, make sure I didn't make a mistake here. Okay, now we perform the antiderivative. This would be negative 18 x squared over 2 plus 26/3 x4 over 4, and we're taking that from 0 to 1. So we're going to get this negative 18 divided by 2 is negative 9, but then I double it, so we get negative 18 1 squared plus, this is going to be 12 on the bottom, but we're doubling it, so it's going to become a 6 on the bottom. So it's 26 over 6, 1 to the 4th, and then the zeros don't factor in. So this is going to be minus 18 plus 26 over 6, which when you create a common denominator, you should get 27/2. And again, use the fact that the last integral has to have numbers on it to get a number for your final answer to kind of help you see the route to go here. So that'd be problem 4. Okay, I was looking at this. I hate when I make little mistakes like this. For some reason, I don't know why this happened. I changed this limit from a 3 to an x. So this should have been a 3. Let's see where that's going to percolate to. So we get 9y minus, that's all still correct, but this is supposed to be a 3, not an x. So we would plug in 9 times 3 minus 3 cubed over 3. This part's correct. So we're going to get not 9x, this should be 27. Not x3, this should have been 27 over 3. Let's just call it 3 cubed over 3. Minus 27x plus 9x cubed, that's all still correct. Okay, now we're going to get 27 minus 9, which gets rid of this x. It's just 18. 27 minus 9, and it's going to make it plus. And then we still have negative 27x, and we still have 9x cubed. Boy, let me just start over from right there. Okay, so this part's wrong, because there's some things we couldn't have combined there. Okay, let's get back on track. Sometimes I like it when I make errors, because then you can see that even math professors make errors. Okay, 27 minus 9 is 18. Then it's going to be minus 27x plus 9x cubed. Here we go. Okay, now we're going to get 2 18x minus 27 halves x squared plus 9x4 over 4 from 0 to 1. So we get 2 18 minus 27 halves plus 9 fourths minus 0 plus 0. And this would be 2 times 18 minus 27 halves plus 9 over 4, which that will become 27 over 2 when you combine, get a lowest common denominator, combine all your numerators, and simplify. Okay, that should be problem 4. Okay, in problem 5, we have another picture to draw. And we have so we have use triple to find the volume of the given solid. The solid enclosed by this cylinder, x squared plus y squared equals 9, and the planes y plus z equals 7 and z equals 1. So the starting one is basically a circular cylinder sitting on the xy plane and going up the z-axis. So this is our cylinder. Now we're going to cut this off at the points z equal 1. So when z equals 1, we're basically going to come in here and slice the entire bottom of this sphere off. So all of that is going to go away. And it's still a circular cylinder, but that bottom one from z equals 1 to the xy plane is gone. So there's a hole there now. Okay, so the new thing looks like this. Okay, so there we go. It's a little bit higher now, the base. And it's going to chop it off at z equal to 7 minus y. So at z equal to 7, use a different color here. Let's say it's right there. So there's z equal to 7. This equation, 7 minus y, is a straight line, and so it's going to go down to y equal to 7 also. So imagine this straight line, but this is a plane. So we've got this angled plane here through 7 and 7. Now we're also going to chop this thing off. Okay, and I don't think there's any hope for me to try to draw what the resultant shape looks like. Actually, it's not super hard to do. Let me see if I can do it. So it's basically this cylinder that's sitting in space, and then it goes up, and then it comes down, like something like that. So it's got this sliced plane off of it, but it would have still been a circular cylinder. Okay, and we're going to have Z is going to go from, I didn't draw this great. Z goes from 1 to 7, and the tricky part is getting X and Y. So let's see if we can do that. So we're going to have, so X, notice that X has to be bound by this circle that has a radius of 3. So the most X can be is minus 3, actually X would be back here, minus 3, and up here at plus 3. Now Y is going to be governed by this same equation. So we're going to have, let's see if we can start putting this stuff in. Y is going to equal plus or minus the square root of 9 minus x squared. So that is the circle on the xy plane. Z is going to be bound by 1 and the equation 7 minus y. And x is going to be bound by negative 3 and 3. So notice x is the only one that's bound by numbers, so that's going to go last. Z is bound by y, so that should go first, which puts y in the middle. So what we're going to have is minus 3 to 3. Then we're going to have minus root 9 minus x squared to positive root 9 minus x squared. Then we have 1 to 7 minus y, and the original equation is, let's see here, they don't have one. So there is no equation to integrate, so it's just going to be the volume, so it's going to be dz dy dx. Now you could do it this way, but it's actually much simpler to switch to polar coordinates, which is what we learned, I believe, in the previous section. So we are going to change this to x is now going to become theta. So if I imagine for the x, I'm going all the way around a circle. So we're going to make this 0 to 2 pi. Y is going to be governed by this circle. So we can say y equals either 1, 9 minus x squared, therefore square both sides, y squared equals 9 minus x squared, add x squared to both sides, x squared plus y squared equals 9. Well, this is the same as saying r squared equals 9 or r equals 3. So the radius is going to go from 0 to 3. Now the hard one is z. Z is going to go from 1 to 7 minus y, but y is really r sine theta, and we know r is 3. So we're going to call this, let's see, we're going to call this 7 minus r sine theta. And dz, dy, dx would change to r dr d theta. And actually we would still have z in there. So z is actually going to be r dz dr d theta. There we go. Okay, so first we anti-derive with respect to dz, but there is no z, so this is just going to be 0 to 2 pi. Radius goes from 0 to 3 of r times z, but we're going from 1 to 7 minus r sine theta. Then we have dr, then we have d theta. So we're going to get 0 to 2 pi, 0 to 3 of r times 7 minus r sine theta minus 1, the lower limit. And so we're going to get 7 minus 1 is 6. So we're going to get 0 to 2 pi, 0 to 3. This is going to be 6 times r, so 6r, minus r sine theta, so it's minus r squared, because I've got to distribute this r to all these terms. And so we get r squared sine theta, and that's with respect to r and then theta. Okay, so we would get 0 to 2 pi. Take the antiderivative, 6r squared over 2 minus r cubed over 3 times sine theta from 0 to 3 d theta. So this would equal 6 over 2 is 3 times 3 squared minus 3 cubed over 3 sine theta. And the lower term, the lower limit 0 is not going to do anything. All those terms will go away. So we have 27 minus 27 over 3. (27 over 3 is 9, so 27 minus 9 sine theta with respect to theta would give us 27 theta minus 9. Antiderivative sine theta is cosine theta from 0 to 2 pi. So we get 27 times 2 pi plus 9 cosine of 2 pi minus 27 times 0 plus 9 cosine of 0. Cosine of 2 pi and cosine of 0 are both 1. So we're going to get 9 minus 9. Those 9s will cancel. This 27, 0 will cancel. So we just get, the only thing that's going to stick around is 27 times 2 pi, which is 54 pi's. Okay, so trick to that one, getting the limits correct, but then switching to polar coordinates, which should save you a lot of energy and effort. Round 5. Okay, for 6, we're going to use the midpoint rule for triple integrals. So we're basically going to turn this 3D shape, and I'm not even going to try to draw it because it's cosine of all 3 letters combined. And x goes from 0 to 2, y goes from 0 to 2, and z goes from 0 to 2 in this case. And basically we're going to change it into a bunch of little blocks. So we're going to make a bunch of rectangles underneath this 3-dimensional shape, and we add up the volume of each rectangle, and that should approximate the volume of this solid. So what we're going to do is we're going to take this region B of cosine x, y, z of this differential volume, and we're going to change it into a summation formula. Let's see. We're going to have the summation. I just linked to the book because I don't know if I want to write all this out. So we have this triple integral, and we're going to rewrite it as Riemann sums. So we're going to sum across the I dimension, j dimension, and k dimension, which is x, y, and z respectively. And we're going to find the midpoints of the function at various points. So let me not write all this. Let me just say this is what we're doing in math speak. And let me show you how to calculate these things. So let's just show you how you would actually do it. Okay, so we're going to have delta V is going to be whatever this number is, and it should be the same for each letter, divided by 2. So for my case, with 2 being the number, you're going to take half of that times, so that's in the x direction, half of this 2 in the y direction, times half of this 2 in the z direction, and for my problem, it's really simple. It's 1 times 1 times 1, which is just 1. Okay, so that's del V. Now the hard part is going to be, we have to find the function, so this is going to be del V times our, del V times our function at various x, y, and z values. So this is 1 times, first we're going to find f when we have 1/2, 1/2, and 1/2. So that would be the exact midpoint of these 3 segments. So from 0 to 2, 0 to 2, 0 to 2, we would do half of each of those segments. Okay, then we would have plus, it's kind of a pattern here, we would have 1/2, 1/2, and 3/2. And then we're going to have the function where we have 1/2, 3/2, and 1/2. So it's kind of like a combination. We're basically finding rectangles at different points along a grid that we set up that's, so imagine you have a block that's 2 by 2 by 2 in 3 dimensions. Well, we're trying to, I think it even says, into 8 sub boxes of equal size. Let me actually draw this so we can try to get a sense for what's going on. Okay, the entire box is going to be 2, 2, and 2. So here is the box. But then we're going to slice that into 8 equal chunks. So we're going to take this half, this half, boy, this is tough to draw, and this half, okay, like that. And so then we're going to slice that in half again. So we're going to have 4 chunks on the bottom. We're going to have 4 of these blocks on the bottom and 4 of these blocks on top. And you basically have to find the x, y, and z coordinates of these blocks. And so this would be, let's see here, 1 unit, 1 unit, and then 1 unit. 1 high, so 1 high, 1 to the y, 1 to the x, but then you want half of those blocks, so it's not like I'm going to the 1, I'm actually going to 1/2, and this would be 3/2, and then this would be 3/2, and this would be 1/2, and this would be 1/2, and this would be 3/2. So each of those little squares within the big square, or cube I should say, has x, y, and z dimensions, but they're all going to be halves or 3/2 depending on where I'm at. So this 1/2, 1/2, 1/2 would identify the very lowest cube, the center of the very lowest cube. So it would be 1/2 in the x, 1/2 in the y, and then 1/2 in the z. So that box, that is the halfway chunk of this little green box down here. I'm just going to circle it because it's getting hard to do. Okay, so that's the first one. And then 1/2, 1/2, 3/2 is the block right above it. So we just found the lower left box and the upper left box. So that's 2 of the 8 boxes we need. Okay, then this one would be x, y, z, so this would be the upper right box. Okay, then we continue with this pattern, and we're going to get 1/2, 3/2, 3/2. So that is actually that might be the top right box. Either way, 1, 2, 3, 4 plus, we've got to do the other boxes. So I have a pattern here, 3/2, 1/2, 1/2. And then we have 3/2, 1/2, 3/2. We're basically just looking for all combinations of these two numbers, with 3 different potential positions. So it's 2 to the 3rd, 8. And then we have 3/2, 3/2, 1/2, and then the last one should be the most closest to us top box, and that would be 3/2 in the X, 3/2 in the Y, 3/2 in the Z. So according to my drawing, that would be the one in the top corner that's closest to us watching on the screen. And lucky for us, the number outside is just 1. So what do we do now? So now we take 1 times, what is the function? The function is the cosine of x, y, z. So it'd be cosine of x, which is 1/2, times cosine of y, which is 1/2, times cosine of z, which is 1/2. And that's basically going to be cosine of 1/8. So this is basically cosine of 1/8. Then the next one's going to be cosine of, just look at these numbers, 1 times 1 times 3 over 8. So it's 3/8. Then the next one's going to be cosine of those 3 numbers, 1 times 3 times 1, which is 3/8. There's going to be a lot that are very similar here. Then it's going to be cosine of those 3 numbers multiplied, 1 times 3 times 3, which is 9 over 8. Okay, that's the top row. Plus cosine 3/8 again. Cosine of this one, which would be 3 times 1 times 3, which is 9/8. Plus cosine of this one, another 9 over 8. Plus the last one, which is 3 times 3 times 3, which is the biggest one, 27 over 8. So if you type that in your calculator and get all those numbers and add them all up, for my value, I get 4.10437, which to 3 decimal places, 1, 2, 3, will stand there, look to the right, too small, cross it off, so 4.104. So kind of a conceptual problem. It takes us actually back to Calculus 1, where we introduced Riemann sums as the first attempt to find volumes underneath curves, and this is just expanding it to 3 dimensions. So kind of hard to draw though. Okay, that's problem 6. Okay, problem 7, a nice easy one. There's no arithmetic to do, it's just process of elimination. So we have this solid formed by dy, dz, dx, and they give us the limits of integration, which is what we have to use to solve which one's the correct curve. So first off, notice that we're looking at y, and y goes from 0 to 4 minus 4z. Well, y going from 4 minus 4z would be equal, this would be equal to 0 when z equals 1. So z can only go from 0 to 1. So that's the biggest z can be. So z goes from 0 to 1. That has to be that has to be the only numbers for z. So that is going to let us eliminate none of these. That's okay. We're going to keep eliminating. We're going to find other ones to eliminate. Okay, now in the z direction, we're going from 0 to 1 minus x. Well, again, that's going to allow z equals 1 minus x and z equals 0. Z equal to 0 is just the xy plane, so they all start there. So that, again, can't eliminate anything yet. But x now is also going to be bound by 1. So the biggest x can be is 1. So this is going to sandwich x between 0 and 1. So now we can start to eliminate. The biggest x can be is 1, so that 4 is gone. The biggest x can be is 1, so that's 4 is gone. So we're down to the bottom 2. Now the last thing, it says x itself will go from 0 to 1, which we already knew. So how can we process eliminate? So if I look at this, can y go to 4? So if y is 4, notice here that if z is 0, then this y would be 4. So from this equation here, this is like y equals this, so y equals 4 minus 4z. At z equal to 0, y equals 4. So that's going to allow us to go all the way out to that 4, which means this 1 is wrong. So it has to be this picture here. X goes from 0 to 1, y goes from 0 to 4, and z goes from 0 to 1. And we just look at the endpoints. You don't have to really think too hard about these equations up here. I mean, we use those equations, but you don't have to worry about plotting them. It just so happens, if you plot y equals 4 minus 4z, you will get this line here, 1 to 4. Okay, that's problem 7. Okay, problem 8, it's also going to help to draw a picture, so I will try to do that now without butchering it. Okay, so it says, find the volume of the given solid. The solid bound by the parabolic cylinder y equals x squared in the plane z equals 0, z equals 6, and y equals 16. So let's start with this one, y equals x squared. That is a parabola that looks like this. And it's going to keep going up. And it goes up until the point z equals 6. So at this height, z equal to 6, it's going to chop this thing off. So, boy, let me see if I can do this without butchering it. So this is going to be, let me go a little higher than 6. So it's like going to come down like this and form a parallel shape like that. Okay, so there's the solid so far. And we've taken care of this and this. Now z equals 0 is just the xy plane. So it doesn't go below this xy plane, so I don't need to draw that. So we've got both of those figured out. Now, y equal to 16. So let me use a different color. Let's go with red. So, and I kind of drew it already a little bit. At y equal to 16, we're forming this plane that's going to come up and chop this thing from going any further in the y direction. So that's when y equals 16. Okay, so we've cut it off on top at z equal to 6. So we've stopped it from going any higher that way. We've chopped it off at the bottom at z equal to 0, so it can't go any further down, it can't go any further up, and it can't go any further towards the y direction because of this red plane here. Okay, so let's see what we're left with. So let's see if we can set up our limits of integration. And we're doing y equals x squared, okay, y equals 16, we got that one too. Okay, so we're going to have, there is no function, so it's just this volume that is described by the limits of integration. So we have, I'm just going to give it to us and then I'll explain why we picked this direction. So dz, dy, dx. Okay, dz is easy, it only goes from 0 to 6. So the start of z is 0 and it goes 6 high. dy, this one's the tricky one. So this dy is actually going to go from x squared. So it starts here. Y starts on this curve x squared. What's the highest y can go? it's cut off at 16. So it's going to stop at 16, this red plane I drew. Now what about x? If y can only go to 16 and y is x squared, then the highest x can ever be is 4, or on the back side, minus 4. So x is going to go from minus 4 to 4. Okay, that's the tricky part. But now that we have that, we can just do the antiderivative. So this is going to be minus 4 to 4, x squared to 16. Antiderivative of dz is z from 0 to 6, dy dx. This equals minus 4 to 4. This is going to be x squared to 16. The antiderivative, I already did it. Z, we're plugging in 6 minus 0, dy dx. So we pull the 6 out. And the antiderivative of dy would just be y. And we're taking that from x squared to 16. Then the dx. This is going to be equal to 6 times the antiderivative minus 4 to 4 of 16 minus x squared dx. This is going to be 6. Antiderivative of 16 is 16x. Antiderivative of x squared is x cubed over 3. And that goes from minus 4 to 4. So we get 6. 16 times 4 minus 4 cubed over 3 minus 16 times minus 4 minus minus 4 cubed over 3. And if you do that and you multiply by 6, you should get 512. So I leave a few steps there at the end for you to do, but I assume you can do powers and subtractions and combine like terms. They're just numbers at this point, so it shouldn't be too bad. And that will be problem 8. Okay, problem 9, they want us to calculate a mass from a density function across this cubic solid. So it says E is a cube, x, y, and z vary from 0 to a, 0 to a, and 0 to a. So pretty similar to that Riemann sum problem where the dimensions in all three directions are the same, so you get a nice solid cube. And we want to find the mass. So the mass is going to be equal to the triple integral of this E region times the density of x, y, z, and then dv. So what we're going to get is we just have to plug in our limits and the density function. So mass is going to be equal to, notice they all go from 0 to a, so I don't really have to be picky. And the density function was 6 x squared plus y squared plus z squared, so I just factored out 6 from each term. And it doesn't matter, I'll just do dx, dy, dz. Since they're exact same limits in the equation, there's really no way to do it what makes it simpler. So we're going to get this equals 6, 0 to a, 0 to a. X is our only variable, so it's going to be x3 over 3 plus y squared times x plus z squared times x. But we're plugging in from 0 to a. So we're going to get 6, 0 to a, 0 to a of a cubed over 3 plus y squared a plus z squared a dy dz. Now we're going to do this with respect to y. So we're going to get 6, 0 to a cubed over 3 times y plus y cubed over 3 times a plus z squared a times y, and that's going from 0 to a dz. So when we plug in a into this, we're going to get antiderivative 0 to a of a to the fourth over 3, so all y's are now a's, plus a fourth divided by 3, plus a squared z squared, dz. Okay, this is going to be equal to 6 times, I've got 2a4 over 3s. Make sure I didn't make a mistake there. That looks right. So it's really 2a4 over 3, but that's a constant, so it's getting a z on it now, plus a squared z3 over 3 from 0 to a. This would be 6. This is going to be 2a to the 5th over 3 plus a to the 5th over 3, which is really 3a 5th over 3, which is 1a. So this is basically 6 times 3a 5s over 3, which is really 1a5 times the 6 gives us 6a to the 5th. So the mass of this cube is 6 times its dimension to the 5th power. That's the mass. Okay, now they want us to find the center of mass. And the center of mass would occur at x bar, y bar, and z bar. So it's like, where could we put something? Imagine if you could balance that cube on a pin that's located at x bar, y bar, z bar, it would be perfectly balanced. Okay, so that's the center of mass. Okay, so how do we find that? Okay, so let me give us the formula for that. So the x bar of the centroid is equal to the moment of inertia in the yz divided by the mass, where the moment of inertia in the yz is equal to the variable x times the mass function. And then y bar similarly is mxz over m, but mxz is equal y times the mass equation. And then z bar is the moment of inertia in the xy. Notice that if I'm x, there's no x in the m term. If it's y, there's no y in the m term. And if it's z, there's no z in the m term. And that's divided by the mass function. But mxy is z times m. Now, lucky for us, there's some symmetry here, so we only have to do one of these, and then the rest will all fall into place. So let's look at this. So let's calculate m. Let's start with this one. Let's just do this one. So we're going to start right here. What is the moment of inertia in the yz direction? Well, it's x times m. Well, in triple integral form, that's going to be 0 to a, 0 to a, 0 to a of everything stays the same except for we're multiplying by x. Oops, right here. So it looks exactly the same as the triple integral we just did, but we added this times x. Now that is going to create a little bit of a different situation. So we're going to have get this 6 can come out, 0 to a, 0 to a, 0 to a, but now it's x to the third plus xy squared plus xz squared. I'm only going to do one of these and I'm going to jump to the answer because otherwise it will take too long. It's not terrible, you just have to do a new set of integrals. The antiderivative of this would be x4 over 4 plus x squared over 2 y squared plus x squared over 2 z squared, and we're evaluating that from 0 to a. But again, you're going to get a4 over 4 and a squared over 2 y squared, so you're going to get a lot of constants with a in it. Now if you do this, you should get myz, and it turns out because of symmetry that all three of these are going to be the same. So myz, mxz, and mxy are all the same, and they turn out to be 7a6 over 2. But then x bar, which is going to be the same as y bar, which is going to be the same as z bar in this case, is that 7a squared over 2 divided by the mass, which is 6a to the 5th. Oops, this is a to the 6th up here. So we're going to get this divided by 2 will combine with this 6, and we're going to get 7/12, a to the 6th on top, a to the 5th on the bottom, and that's just going to give us 7 over 12 with only one a left on top. That will be the x bar, y bar, z bar. So there are quite a few steps I skipped in getting the moments of inertia, but the approach is exactly the same in how we found the mass. You just have to go through and be very careful about accounting for your powers and your letters and everything. Okay, so that's problem 9. Okay, for problem 10, they want us to find the average value of a function over a solid region E. And they give us this equation here. And E is the region defined by, it says, let's see here. The function is 3x squared z plus 3y squared z over the region enclosed by the paraboloid z equals 4 minus x squared minus y squared, and the plane z equal to 0. So I'm not even going to try to draw that. What we're going to get is we have, first we have to find the volume of E. We're going to find this term right here. And that in itself is a triple integral. And it's going to just be of, and I'm going to give us what it should become, dz dy dx. And we're looking at this function, and the plane z equal to 0. So the first thing z is going to go from 0 right here to this, 4 minus x squared plus y squared. So notice I factored out a minus here and made that plus. Okay. Y is going to go based on this x squared plus y squared. If you rearrange that equation, you'll get y goes from minus 4 minus x squared to positive square root 4 minus x squared. And then finally, x is going to go from minus 2 to 2. Okay, so this is like a, well, it's a paraboloid, so there is some symmetry here. Now, what we're going to do is we are going to take the antiderivative of this with respect to z. So we're going to get this volume goes from minus 2 in the x to positive 2 in the x. And then it goes minus square root of 4 minus x squared to positive 4 minus x squared. And then it's going to be z from 0 to 4 minus x squared plus y squared. And then it's dy dx. So that's going to give us plug that into z and I'll just get 4 minus x squared plus y squared. And the 0 lower limit will go away. Well, this looks really similar to a problem we did earlier. What we wanted to do at this point is switch to polar coordinates. So we're going to notice that x is going from -2 to 2, so that is going to give us a full circle, 0 to 2 pi. Then this is really saying x squared plus y squared equals 4, or the radius is going to go from 0 to 2. So maybe I should show that. So this y limit here is saying y equals 4 minus x squared, square both sides. It's very similar to what we did before, still minus. Add x squared to both sides. This is saying r squared equals 4, or r equals 2. So r will vary from 0 to 2. Now we have 4 minus, this is r squared. And then we're going to have dy dx will change to polar coordinates, which are r dr d theta, which will give us 0 to 2 pi. Take the antiderivative of this with respect to r. First, let's distribute this r. So actually, let me write one more step. This will be 4r minus r cubed dr d theta. This will equal 0 to 2 pi of 4r squared over 2 minus r4 over 4 from 0 to 2. And that's going to give us 0 to 2 pi. This is going to be 2 squared is 4 over 2, which is 2 times 4 is 8, minus 2 times 2 is 4, times 2 is 8, times 2 is 16 over 4, which is 4, d theta. So we get 4 antiderivative 0 to 2 pi of theta, and that's just going to be 4 times 2 pi minus 0, which is 8 pi. And that is just this term I circled. So the average of this is going to be 1 over this volume, which is 8 pi, times the antiderivative of the new one, which is going to be this function. So let's see what we got here. We're going to have very, very similar. We're going to get yeah, I think I want to jump the gun a little bit. So it is, let's just jump through this a bit. I could write -2 to 2 and square root, like we did before, but let's go right to polar coordinates. So this is going to go from 0 to 2 pi, 0 to 2. Now the z term is tricky. The z term is still 0 to 4 minus r squared, but we actually have 3x squared. Now we have a function in here. 3x squared z plus 3y squared z. dz d. See, this is where I probably shouldn't have jumped ahead. dz, let's not make this r yet, minus x squared plus y squared. dz, but then it is r dr d theta. Okay, notice that there's a common z between these two. So we're going to factor this out. We're going to factor out z, 3z, and what's left is x squared plus y squared. And then we have dz r dr d theta. And let's factor out this 3, and we'll get the antiderivative. So we get 3 over 8 pi, 0 to 2 pi, 0 to 2, and I forgot the the integral sign here. There's an integral. It's this same integral sign. I just forgot to write it. This should still be right in front of the 3. Okay, so I am taking the antiderivative now and plugging in those limits. So it's going to be z squared over 2 from 0 to 4 minus x squared plus y squared. And then we have another x squared plus y squared. And then we have r dr d theta. But this is where I'm going to start to do some simplifying. This is really r squared. This is really r squared. But we're also squaring this. So what do we get? What is the problem? This is equal to 3 over 16 pi, so I pulled this 2 out, times z squared, which would be 4 minus r squared squared, times another r squared, times another r, then dr d theta. Let me just check, because that's a lot. R squared, 4 minus r squared, times another r, dr d theta. 3 over 16 pi. Okay, this is correct. Okay, you've got to FOIL this and distribute the r squared. And notice I completely dropped my limits of integration, so there's still a double integral here. So we're going to end up with 3 over 16 pi, 0 to 2 pi, 0 to 2 of 16 r cubed minus 8r squared times 8r to the 5th plus r to the 4th plus r squared, but square r to the 4th, 6, 7, plus r to the 7th, dr d theta. Okay, and believe it or not, when you plug in, when you take the antiderivative of this and get r4 over 4 and r6 over 6 and r8 over 8, and you plug in from 0 to 2, this whole thing is going to simplify to simply 3 over 16 pi, 0 to 2 pi of a constant, 32 over 3. These 3's will cancel. 32 divided by 16 is 2. So we get 2 over pi times the antiderivative of d theta from 0 to 2 pi, which is just 2 over pi times 2 pi minus 0, which is equal to 4 pi over pi, which is 4. So all that work, and we get the answer is 4. And that will complete section 15.6.